Welcome back to the second lecture about non-experimental designs. In this lecture, I'm going to talk to you about relational designs. I'm going to start with comparative designs, where I'm comparing groups, and then I'm going to talk again about correlational studies, where we're showing a relationship between different variables. So comparative designs first. With a comparative design, you have an independent variable condition for one group, and you have a different condition of state or amount of that independent variable for another group. And then what you want to do is compare the differences of the outcomes or the dependent variables for the two groups. And with a comparative design, you're focusing on those different outcomes for the two different groups. With a comparative design, you cannot suggest that the independent variable condition causes the dependent variable or the outcome that you get. You need to be very careful about that. All you can do is report the differences and then make some suggestions or some inferences. So some examples of this. If Classroom A uses this math program and Classroom B does not, will the two groups have different means on their semester exam? So if you find that the math scores for Classroom A, where they use that math program, are significantly higher than those from Classroom B, you can say that there's a relationship between the math program use and achievement. You cannot say that the math intervention or this math program caused the scores to be higher. So you're looking for the differences in order to between the groups to show a relationship between the independent variable and the dependent variable. Some other examples, teacher efficacy. You may want to know if teacher efficacy is higher among elementary teachers than secondary teachers. And if you find that there is, you can then safely say there's a relationship between the level teachers teach at and their sense of efficacy, of teaching efficacy. So that's another example. You're trying to show a relationship by comparing the groups. Now there's one type of comparative design that we call causal comparative or ex post facto. And from this type of non-experimental design, we can sometimes imply that causation happened or that there's a causal relationship even without experimental design. So when a researcher looks at data from existing conditions and compares the groups after the conditions have played out, that's an ex post facto design, and it's valid to imply causation. It's not experimental. There was no random selection or assignment to conditions. You just used existing groups and gathered data to describe what happened. Basically, you have Group A and Group B, and you compared the outcome. So you're using data that happened naturally, and you're reporting the effects that you think the independent variable had or on an outcome or a dependent variable. One thing you need to look for as you read these kinds of studies, there is a treatment or an intervention group, and there's a comparison group. It should never be called a control group. And you will sometimes hear these or read these designs called quasi-experimental. Now, when we're in the first example here on this slide, well, let me start first of all. The purpose of an ex post facto design is to investigate a causal relationship when the experimental design was not possible. And I talked about reasons for that in the previous lecture. Maybe it's not ethical to withhold something from a group. So here's two examples. Does a new instructional coaching program compared to a traditional PD program influence teacher effectiveness? We study that all the time. Does preschool participation affect first grade achievement? So do children who had a preschool experience do better or worse in first grade than their counterparts who didn't. So in this first example about the coaching program, it would be really important to collect good data on the quality of the two programs we're comparing, the fidelity to those programs. In other words, were they implemented as they were designed, and were they implemented fully, or was there just lip service and somebody said they were doing it but they really didn't? And there are obviously a lot of other variables that are not being considered in this first example. Maybe teachers hate the instructional coaching, an instructional coaching program, and they prefer the traditional PD program. Whether or not they could, and that would have an influence on teacher effectiveness. Teacher time may be a factor. The availability of coaches. The principal may hate the traditional PD program. That's all going to influence teacher effectiveness. Now in the second example, it's pretty obvious that we couldn't randomly assign children in the United States to preschool or not to preschool. And you can also see a lot of other factors that could influence the achievement of first graders. It would be really hard to say it all came from their preschool experience or not. In these ex post facto designs, you collected the data after this had all played out naturally. It's not the same as a convenience sample because you're not even sampling. You're simply taking existing groups, but you're taking these groups because they differ on the amount or the level or the whether or not they have this independent variable. That's not the same as a convenience sample where you just grab a group of people and then you survey them or you do some kind of experiment with them. Ex post facto and causal comparative are used a lot in educational research. When you're looking at causal comparative or ex post facto research designs, you will see that there's a presumption that the causal condition already occurred. So there's a time factor. The other variables should be considered, and there are ways in these studies where a researcher can actually, using statistical analysis, actually control or take out the effects of some variables. And you will see that it'll, I did such and such and I controlled for socioeconomic status or gender or age, and that means that I'm removing the effects statistically when I say that I'm controlling for something. We also have to acknowledge the differences between the groups. So very often in these studies, there may be a pretest. Two groups are given the same pretest. And you say the mean from this group was 37 and the mean from this other existing group was 42. And then you have to run the analysis to find out if those are statistically different, if there's a statistical significance in the difference of those two scores. If there's not, you're fine, you're good to go. You can say the two groups are pretty well equivalent. But if there is, then you have to go up and statistically control and remove the effects of the one group doing better on the pretest than the other group did. So with all these different things that we have to do, we have to be cautious about our conclusions about cause. Controlling for differences in groups is not the same as randomly selecting those groups and having the variability be a function of the randomness of our selection. So be very cautious about that. Now, when you're critiquing these kinds of studies, you need to look very carefully at the description that's given of the participants and the instruments used, because remember, that's what you're using. Those descriptive statistics are really important to know whether these groups were even equivalent. Were the instruments used for measuring even worth reading about? You need to look very carefully for what that independent variable is and how it's operationally defined, and then the levels or the conditions of it. There should be really clear criteria for identifying those different groups. The groups were This one was chosen because they got no physical activity during the day, and this group always got it. Some kind of that clearly shows the two groups are different on the independent variable. Remember, if you see that there's some kind of inference about causation, you need to take that with caution. And one final point, you need to be really, really careful when looking at graphs. And let me give you a couple of examples. I love these. One of the most famous examples of manipulating graphs actually came out of the UK. And the graph on the left was used to report this horrible increase, this massive increase in house prices this year. And when you glance at that, it does look like a huge change. Now, when the same change is put on a different scale on the right graph, you don't see the excitement for a massive increase in house prices. So that's one of the ways that graphs get manipulated or represented. And I'm not sure that this is always done consciously, but I've seen a lot of research where the author is like just so obviously excited about this massive difference between these two groups. And sometimes if the graphs were just done differently with the scale, the difference wouldn't be there. Here's another example that may be more education related. So Class A, this is a graph showing the report of their grades on a test, the percent that they got correct. On the right is Class B on the same exam. And when you just glance at these two graphs, Class A looks very different than Class B, and they're not. The mean is the same, the range is the same. If you were to look at the skewness, everything would be the same for these two classes. But what's happened is on the left, the scale starts at 65, or is that, yeah, starts at 65 and goes up to 80. And look at the increments. They're in increments of what? They kind of bounce all over the place a little bit. So on the right, the scale goes from 0% correct to 100. So if we changed the scale on Class A to be the same as Class B, the two graphs would look very, very similar. And at a glance, you would be able to see there was not much difference between these two classes. Now, we're going to move on from comparative to correlational designs. And this will be a little bit of a review because remember, relationships and showing correlations are ways of describing what is. So they're a descriptive statistic that we can use. So this is going to be a bit of a review, but I think we'll take it a little bit deeper for you. Correlational research designs are set up to describe the relationship between two variables, and that's called bivariate, or a combination of variables, and that's called multivariate. In a correlational design, you will see a label of an independent variable and a dependent variable, but there's really no true distinction between which one's the independent and which one's the dependent. Usually, the independent precedes the dependent in time, or sometimes it's just common sense that the relationship would go that way. So here's some examples of some questions, and the first two I want you to look at really carefully. Are scores on math achievement tests associated with math attitude scores? Really hard to say which one of those would be the independent variable and which one's the dependent variable. Because look, in the next one, I just switched it around. Are scores on math attitude measures associated with math achievement scores? There's no true independent variable and then dependent variable. All we want to do is show the relationship between the two variables. And then another example would be, is there a relationship between the years of teaching experience and teacher efficacy? One of the ways that correlational designs are used is to answer questions about prediction. we can use the relationships that we find between two variables to pretty confidently make predictions. And then what we do is with the variable that we consider to be the predictor, and it's sometimes called the antecedent, takes the place of the independent variable, and then you have a criterion or an outcome that is like the dependent variable. And with prediction correlation designs, of course, there's always a time interval. And remember, these aren't experimental. You're not assigning groups or anything. You're taking data that's there because of some naturally occurring phenomena. So some examples of questions that go along with prediction. Could parent education level be used to predict the reading comprehension of first graders? Do you think there's a relationship there? Could it be used to predict? Could I look at the parent education level and make a pretty solid prediction about how that first grader is going to read? I'm not saying there is, but that's the kind of question I could answer. A non-education one that will make sense if you go to the grocery store. Can yearly rainfall in the Midwest be used to predict what beef prices are going to be 6 months later? So we can take information that we have pretty solidly, we can know this, and then we can make predictions about what's going to happen in the future from them. Now, correlational designs can make predictions with just simple regression. So here I've got a scatterplot. You'll remember these from the lecture about descriptive statistics. And what I'm looking at is the number of books that children read each year. So I took 106-year-olds, 107-year-olds, 108-year-olds. I mean, those sample sizes would be ridiculous, obviously. But I took the average, and what this graph shows is that on average, 6-year-olds read 2 books each year. 7-year-olds read 3, 8-year-olds read 3, 9-year-olds read 5, 10-year-olds read 6 books a year, and so on. And I looked at then the average number of books that these age groups of kids read. Now I want to predict with that. So what I do is I add a trend line that goes up through the middle of that scatter plot, and then the dotted line extends it beyond my sample group. So this lets me predict that 13-year-olds, I go up from 13 and hit that line, it looks like 13-year-olds will probably read 10 books in a year. If this linear trend holds, I can predict that. And it also lets me predict that in another group of 10-year-olds, they will probably, 10-year-olds, they will probably read 6 books a year. So I can use the data that I've got to predict what's going to happen in the future. Now, simple regression is great and you get a linear trend. But then there's an analysis with correlation that's called multiple regression. And that means that you're using more than one predictor. We're not just using the child's age to predict how many books they would use, but we'd be using other things. Maybe the socioeconomic status of the parents, maybe the language that the children speak at home, anything like that. And you would make this combination of predictors. So predictors can then be combined in two different ways, and we can get 2 really important pieces of information out of this as we predict. First of all, we can combine those predictors to make an overall prediction. So if I take several factors, I can predict what will happen. And that's called the coefficient of multiple correlation. Remember, we had a correlation coefficient that shows the relationship just between 2 variables. But this is showing the relationship between a group of variables and an outcome. Further, we can go deeper and we can actually extract the importance of each of those predictors in the combination. And that symbol is a beta, and it's called a beta weight. Then, when I've got all of that, and I'm going to give you some examples and go deeper into this, so don't panic yet. We'll go slowly. I can actually statistically control out for certain variables. So in studies, you will read statements like this. After controlling for SES, socioeconomic status, the parent education level explained 26.4% of the variance in math achievement. So translated, that means that the researcher took parent education and SES, put them together, and found a relationship with math achievement. Then the researcher went in and peeled away the socioeconomic status and was left with the amount that could be explained by the parent education. Let me translate that again. This statement, the researcher took socioeconomic status and parent education level, put those together to predict what the math achievement was going to be, or to explain the math achievement of the students. But then the researcher went deeper, peeled away the socioeconomic status, and was left with over 26% of the variability in math achievement could confidently be explained by the parent education level. Let me give you some more examples. Let me use an example that has nothing to do with education, but it'll make sense to any of you who have to pay for car insurance. And if any of you have teenage boys driving, you will really get this one. With multiple regression designs, you can list out the variables that may influence an outcome. So if I want to know the outcome, what's the probability of an accident with property damage? And I list out on the left all of the variables that probably could explain that probability of accidents happening. I could look at the age of the driver, how many years of driving experience the driver had, whether this driver had driver's ed classes, the gender of the driver, the ethnicity of the driver, and you can think of others. But say I've researched and I'm an insurance company and I've come up with these 5 factors that seem to probably predict accident with property damage. So what I do is I combine all of those and see if there's a relationship or a correlation with that probability of accidents. So perhaps altogether, these 5 factors account for 75% of that probability of having an accident. That would seem reasonable, wouldn't it? But then I want to know, well, which one of these is the most important? Because I want to charge you an amount of money each month based on these factors, and I want to weight them as I come up with your bill. Well, of that 75%, maybe age is related to 15% of the variance. Years of experience, 52%, driver's ed 3%, gender 4%, and ethnicity 1%. Then the insurance company can weight your bill based on your age, years of driver's experience, driver's ed, gender, and your ethnicity. And most of your bill in that case is going to come from your years of driving experience. Now, this is extremely simplified. Don't think you're going to go and become an actuary on this little example, but it helps you to understand how we take variables and we combine them to see if there's a relationship with something. And if we find a relationship, we then can weight each of those variables to see how much of it is the influence of that variable. Now let's imagine an education example. Perhaps I want to know which factors influence a student's score on the end of course test. So, high school Algebra 1, the end of course test, or biology in high school. Those are end of course tests that we use, and they are becoming very important in some high stakes testing, especially in our state. So I could list out all of the variables. All of this has to be based on research. You don't just start making a list of variables and guessing. You have to do your lit review and figure out which ones are worth studying first. And so I list out the things that probably have a relationship on how a student does on a final exam. But if I'm particularly interested my research is looking at the influence of peers. I'm going to focus on those first 4 variables there that are probably related somehow to the peers of the student. So the class average, the class that the student's in, the average grade that that class gets, does that have anything to do with any relationship with the scores the students get on the end of a course test? Does participation in a sport or a club after school, some kind of social event, does that influence the scores on the end of course test? Gender, ethnicity, the culture that a child's growing up in, does that, those kinds of peer influences. Then I've separated out everything else, that the parent education level, the homework hours, the teacher experience, previous grades, etc. The things that my research has shown aren't related to peer influences. So I separate these into 2 groups. So then when I run my analysis, suppose I find that 26% of the variance in the scores that kids get on the end of course tests is related to those 4 variables that have peer influences in them. So I've got this 26% that this relationship I found. I can then drill down and see how much each of those variables contribute to that 26%. I can analyze which of those variables is the most important in explaining the end of course test, the variability in student scores on those end of course tests. And then if there's one of those variables I'm especially interested in, I can statistically remove the influence of all the others. Now, when I run my analysis, I would find that 26% come from those first 4, and the other 74% is explained by everything else. Now, what's really weird about this is in educational research, we get really excited about being able to explain even 26% of the variability of an outcome. There are so many factors that go into something like the score on an end of course test that we really honestly jump up and down and throw a party for 26%.